In this PowerPoint recording, we will look at the different functional groups encountered in Organic Chemistry 1 using infrared spectroscopy. So as we see on the slide here, there's a couple different sections of information that we'll walk through first, and then we'll go through each different functional groups, pointing out the main diagnostic signatures. So as we see in the table to the upper left here, there are three regions, 1, 2, and 3, and they'll be color-coded in this IR spectrum below it. So region 1 is blue, region 2 will be red bar, and then region 3 will be in green. So to the right of that is a movie that was made in an app called iSpartan, which will give you an idea of what you're actually seeing when you see the signal in the IR spectrum. So in the simulated spectrum below, you'll see a little bar move over, and then you'll actually see the bond stretching in the movie that's being played. So our first functional group is the alkane, and really the only thing we're going to encounter is C-sp3 H bonds in the 3000 to 2800 reciprocal centimeter region, and these are classified as a strong intensity and very sharp peaks. So as you're reading the x-axis from 4000 down to about 500, region 1 is going to be what I call XH stretching, and that's specifically carbon H, oxygen H, or NH. So in the alkane region, we just have sp3 hybridized carbon H stretching, and you see that from 100% transmittance as the laser is scanning, and then there's absorption, and you see some strong intensity that essentially reaches 0% transmittance. The peaks go back up pretty quickly, and overall we say they're a sharp shape. So let's go ahead and look at the movie of this, and we'll see as the movie progresses. We've identified some bonds that are going to stretch now. So there's CH stretching there in the 3000 region. We'll move along these other signals. And so what you're seeing are different vibrational modes. So for example, asymmetric stretching. Now there's some symmetric stretching of the CH. And essentially in region 1, you're most likely going to have sp3 hybridized carbon H stretching in every molecule you see. So those are really not terribly diagnostic because every molecule is going to have them. So moving on now to the alkene functional group, and so this is monosubstituted alkene. We can see in region 1 we're going to have an sp2 hybridized carbon H stretch that's moved a little bit to the left of the normal alkane stretching, so you can see it there. So we would say the intensity is weak because it's not going too far down in terms of the transmittance or the absorbance, if you're thinking that way. But the peak is sharp; it goes down and then right back up. Region 2, there's no peaks. Region 2 is the triple bond region, and then this should be region 3 in green, from 1700 to 1500. There's going to be some weak intensity stretching of the alkene bond. So let's go ahead and play the movie here. And you'll see immediately that's the sp2 hybridized carbon H stretching of the alkene. Again, offset from the normal alkane stretching, which you'll see after we get done with the alkene. So there's some more sp2 carbon H stretching. Now we're in the alkane region below 3000 here. And so again, those are just the different modes. Here's the actual CC double bond stretching. It's showing it at 1674 in the simulated spectrum. But again, keep in mind, carbon-carbon double bond stretching is not going to be very strong on the actual spectra that you see. So moving along now, we have a cis alkene functional group, and the molecule that we're looking at is cis 2-pentene, is shown in this spectrum. And again, this is obtained from the website SDBS. You can just go in and do a keyword search for alkene. So this one is a di-substituted alkene with the cis geometry. So region 1, again, we'll see that sp2 hybridized carbon H stretching is a weak but sharp intensity, nothing in region 2, and then region 3, the double bond stretch. So let's watch this movie. So, and again, as we move along in the simulated spectrum, you'll see these different vibrational modes. For example, symmetric stretching. Now there's the alkene. And the reason that the intensity of a signal would be weak is because the IR is interacting with the dipole moment of the bond between the two atoms. So in this alkene, there's not a big difference in electronegativity between those two atoms, so the dipole moment is not big. There is one, but it's small, so the interaction of the IR with it is very weak. So now we're going to look at a trans alkene. So this compound is trans 2-hexene, again, with the data harvested from SDBS. The structure is shown down here. It has the sp2 hybridized H stretch in blue, but you can see it's merging into the sp3 H stretching. The CC double bond stretch is a little bit more prominent here. Again, the dipole moment overall is probably bigger for the trans geometry versus the cis. So let's go ahead and watch this movie. Again, you see overlap between the different stretching modes. That's why you see these other bonds stretching. And again, if you think about the uniqueness type of the hydrogen sets, that's why you see a lot of different peaks in that region, because they're all going to have their different vibrational modes. So let's move on. Now we're at a terminal alkyne functional group. The molecule is 1-hexyne, and the structure is shown down here. The table here again, this is from SDBS. That's the numerical value of the wave number, reciprocal centimeters, and then the percent transmittance shown here. So now we see that the sp hybridized carbon H is really shifted left of the normal alkane CH stretching. So that's pretty intense. Strong, sharp CH stretching. Again, this is for a terminal alkyne. And then we have a pretty weak CC triple bond. And again, that's the difference between the electronegativity of the two atoms is not great, so that leads to the weak intensity. So the molecule simulation here, you're going to see that pretty strong C sp hybridized carbon H stretching. Now your normal alkane CH stretching. And then we'll move over to the triple bond. And again, now the triple bond is in region 2, highlighted in red, 24 to 2200. So region 2 is your triple bonds. So now moving on to an internal alkyne. Notice the nomenclature here. Again, this is the major diagnostic functional group for that for that bond pattern. And this says none. That does not mean, for the alkyne you see nothing, because you're still going to see the normal sp3 hybridized carbon H stretching. So here we have 2-hexyne. The double bond is internal now, so there's not really a great difference in electronegativity, so that's why you don't really see anything in region 2. Region 1 no longer has that terminal CH, so you just have your normal alkane looking stuff in this molecule. We'll go ahead and play the movie where you see those stretches occurring, different vibrational modes. The sp3 hybridized carbon H stretching. And then we'll go ahead and move on. Now we're at our first functional group with a heteroatom. This is a primary amine, and the structure from SDBS is butylamine, so a 4-carbon chain with an NH2 group at the end. We can see now in region 1, the NH2 group is shifted left to the normal alkane stuff, so it's over here from 3,800 to about 3,000. It's strong, and we call it very broad, so it gradually is increasing. We see this sort of doublet looking structure that corresponds to the 2 hydrogens of the primary amine. And we'll go ahead and play the movie here. You see the NH stretching, that would be a symmetrical stretch. Your normal alkane stretching. So we'll go ahead and move on now to the alcohol functional group. So in region 1 we have the OH stretch. It's very strong and very broad. So when we say broad, we're talking about basically the width of the signal. So that's pretty broad from one side to the other. And the intensity, it's really going down, a strong absorption, and then it's coming back up in a nice smooth, almost looks like a parabola pattern, with some separation really from the sp3 hybridized carbon H stretching. And so this is 1-propanol, and let's watch the movie for that. There's the OH stretching, very strong. Then it'll move into your normal asymmetric and symmetric stretching, and again, you see a lot of those signals because there's different uniqueness sets of these CH types here. So we're going up an oxidation state now from the alcohol to the aldehyde. We have a 4-carbon aldehyde, butyraldehyde. Now there's the diagnostic signatures for the aldehyde occur in region 1, in region 2. So this is region 3 in green. So we have the carbonyl stretch, which is strong and sharp between 18 and 1700. That coupled with this sp2 hybridized carbon H stretch that is now to the right of the normal alkane stretching is indicative of the aldehyde. So the aldehyde functional group is the only carbonyl one that's going to have this signal to the right. So let's watch this movie. There's your alkane CH stretching, different vibrational modes. Now we're off into that aldehydic CH stretch, very intense. Here's the carbonyl CO double bond stretch, and again that's region 3. That's where you're typically going to see your carbonyl stretches. And then within that region of all the carbonyl containing functional groups, there's going to be some specific things we can look for that'll help us pinpoint exactly what functional group they are. So we're now in the ketone. Notice region 1 and 2. Again, region 2 is your triple bond. Region 3, your CO double bond. We can see that this molecule is called acetone. A nice sharp carbonyl stretch. So again, when you're interpreting the IR data, you're looking for really heteroatom containing functional groups, because this is organic chemistry. Every molecule is going to have carbon-carbon bonds, carbon-H bonds. So you're looking for these heteroatom containing functional groups such as the ketone. There you see the CO double bond stretch at 1763 in the simulation. So if you see that signal, you can say, okay, that's a carbonyl. It's 1 degree of unsaturation. It has an oxygen. And then you can start figuring out what else is in the molecule. So now we're going up in oxidation state to oxidation state 3 with a carboxylic acid, which is going to have an OH and a carbonyl, and this molecule is called propionoic acid. Here's the structure here. So region 3, you're going to have your carbonyl stretch, and then region 1, you're going to have an OH stretch, but notice this OH stretch looks different from an alcohol in that it's merged into the normal alkane stretching. It does not go back up like the alcohol did. So these two pieces of data in region 1 and 3 are really strong indicators of that collection of atoms here of the carboxylic acid functional group. So you can say, if you see that, okay, the molecule has to have CO2H as part of the molecular formula. There's the OH stretch. Your alkane stretching, and then now your carbonyl stretch. So in the simulation, this one's at 1789. And again, the app iSpartan is calculating that spectrum using equations based on empirical evidence of where these signals are observed in the actual spectrum. Okay, so moving on now to the ester functional group. Basically, an ester is a carboxylic acid derivative where the hydrogen of the OH has been replaced with carbon. So in this molecule, propyl acetate, really what we're now seeing is just the carbonyl in region 3, and those usually typically occur about 1750 reciprocal centimeters for esters. So again, notice there's no OH stretch because we've replaced the H with carbon. And so let's watch the movie for this. Here's your CH alkane stretching of different vibrational modes. We're now in the carbonyl stretch. This is showing it at 1771 in the simulation. So we'll move on. Now to the anhydride functional group. This molecule is propionoic anhydride, and what that is a linkage of two carbonyl functional groups through an oxygen. So it's anhydride basically because it's the condensation of two carboxylic acids together with the loss of a water molecule, H2O, across the carbonyl groups here. And in region 3, we see this doublet-looking structure of the two carbonyls. One of them is going to be a symmetric stretching, and the other one will be an asymmetric stretching where the groups are out of phase. So let's look at that simulation. So this is what looks like a symmetric stretching, and then when it moves over to the other doublet, this is an asymmetric stretching where they're out of phase. And we'll move on now to the acid chloride functional group. An acid chloride is shown in this molecule, acetyl chloride. is at oxidation state 3 of the sp2 hybridized carbon, and now it has a sigma bond to a chlorine. So regions 1 and 2 we see nothing. Region 3 of the carbonyl is usually at 1800 exactly for carboxylic acid. Now again, it doesn't really matter what is bonded here at the alpha carbon. The COCl elements of the acid typically are at 1800. So let's look at this. So there's your carbonyl stretching. Yes, there is a C-Cl bond, but that is going to occur below 1500, and for all intent and purposes in our class, we're not really going to consider anything below 1500 to about 500, as that is the fingerprint region. And it gets a little busier, so it's harder to interpret things, which is beyond the scope of Organic Chemistry 1. Now we're looking at a carbonyl group with a nitrogen bonded to it, so a primary amide. And now in region 1, we're going to see the NH stretching, and so this is very broad and intense. There is a doublet-looking feature to it due to the 2 hydrogens bonded to the nitrogen. And now with an amide carbonyl, the CO stretch is going to occur below 1700, as seen in this molecule called acetamide. And the reason that the amides have the carbonyl below is due to resonance delocalization of the lone electron pair on nitrogen up into the oxygen. So this double bond character decreases, sending that signal below 1700. So there's an asymmetric NH stretching. There's a symmetric NH stretching, the normal alkane stretching in this region here, region 1, and then we're going to move to region 3 to see the carbonyl stretch of the amide. So again, keep in mind the simulation does show it at 1758. But in reality, it's almost always below 1700. So again, the simulation is not accounting for factors such as resonance. Now here we're moving on to the secondary amide. So notice we still have an NH stretch, but it's no longer a doublet looking feature because there's only one NH group of the secondary amide. And that classification comes from the nitrogen being bonded to 2 different carbons, as we see here in this molecule, N-methyl acetamide. And again, region 3 is going to have the carbonyl below 1700. So let's take a look at this movie. So the important learning objective when you're interpreting IR spectra is to always keep in mind that even though the spectrum is a snapshot, in reality what is happening is the IR light is perturbing the dipole moment of that functional group bond. So that's why you're seeing the response in terms of the spectrum. So moving on now. To a tertiary amide. So we no longer have any NH bonds to the nitrogen. So we have 1, 2, 3 carbons. That's the tertiary classification. And this is NN dimethylacetamide with the carbonyl stretch again being below 1700. So as you're interpreting these clues, you're putting together, you're building a picture of the composition of the molecule. You see a signal below 1700, you can say, okay, there's a CO carbonyl, there's probably a nitrogen as well, so I have a carbon doubly bonded to oxygen, and that carbon is singly bonded to the nitrogen. So you have 3 different elements accounted for. You have a degree of unsaturation in the carbonyl group, and that can help you start constructing a molecular structure from those elements. The final functional group in this short PowerPoint here is the nitrile, and we're looking at acetonitrile, and this is where we see a signal in region 2 that's very strong and sharp. The CN triple bond, the nitrile, or otherwise known as cyano group, you can see that it's really intense, really sharp, so down and back up in terms of the intensity. And so in this movie, we'll see that in region 2. There's your normal alkane, CH stretching. Again, different vibrational modes. We're zooming in here. Now we're moving over to the CN triple bond stretch. And so when you see a signal in that region, again, you're going to have to use other clues to differentiate between the alkyne and the nitrile. But there's ways to do that, but this is indicative of a triple bond. And so to wrap up, this PowerPoint has been a discussion of the major functional groups that you'll see in Organic Chemistry 1 and 2, using infrared data to confirm their major diagnostic signatures.